So here is another example where you have a compound containing nitrogen, carbon, and sulfur. Which one of these structures should it be? Well, here you've got this sulfur right here is 1, 2, 3, 4, 5, 6, so that's 0. 4 on the carbon, that's 0. 2, 4, 5, 6, that's 1 extra, so that's a -1. This formula right here, doing the same type of calculation, this would have a -2 because it's got 1, 2, 3, 4, 5, 6 around it. This nitrogen has 1, 2, 3, 4, so it's missing 1. That's a +1. And this has 1, 2, 3, 4, 5, 6, so that's a 0. This right here, -2 again. This would be a +2, and this would be a -1. So the rule for selecting what structure it would be is to find the one that has the lowest overall value, and that would be this one right here. Now, you also can look at another example. You've got N2O, right? So here you've got a +1 for this nitrogen, a -1 for this one, and a 0 here. This would be the preferred structure over this one right here where you have +2 and 2 -1s over here. Okay? So this would be the preferred structure. In this example, you've got the possibility of being either this one or this one, right? They both have the same formal charge on them. And what happens is it's actually a combination of the two. And so these are called two resonating structures. A compound resonates between this one and this one. It doesn't mean that at any one time it's this or it's this. It means that at all times, it is sort of a mix between the two. But we can't represent that easily. And so what we do is we do it this way and then put a little arrow here with a caret here, the arrow, and then the caret this way, right? That's how that sort of thing is represented. These types of arrows right here is what I was talking about. The same sort of thing happens here, where you've got a carbon with 3 oxygens. For it to be satisfied, you've got to have 1 double bond and 2 single bonds. That double bond could be here, or it could be with this atom or with this atom. So you see that there are 3 different resonating structures. And the thing is, when you have more than one resonating structure, that makes the compound quite a bit more stable. That brings us to another question. The strength of a bond. A single bond has 1 energy. If you have a carbon with an oxygen bond, and there's just a single one, that bond has less strength than if you have a double bond, and a third bond makes it even stronger yet. So this right here, I can tell just by looking at it, that breaking 1 bond here and breaking 3 bonds here is going to give you a lot of energy because you are forming these CH bonds here and then 1 bond here. So the OH here is formed, a CH and a CH and a CH is formed out of this particular one. And so this right here is going to have a lower energy than these two, and so you are going to get a lot of energy released in this sort of a reaction. How they do that is they look at it in the following way. It's called the Born-Haber cycle. And what it does is a stepwise, how much energy does it take to get from one step to another? If you've got the overall change from this material to this one is this amount right here. So here what you have to do is you take the solid here and the gas, and you've got to first change this to a gas, right? So it can react. Once you've changed this to a gas, what you are then doing is you are raising that up to a certain energy level, okay? So that you can have this ionized. Then you raise it more yet so that what you're doing is you are then getting this material formed. You're okay, so that you're losing 1/2 of that. Then you are coming down, forming these two together. This ion is formed, and then from these two ions you get this solid. So this is the lattice energy. This is the electron affinity energy, giving, in other words, because it has to give up this energy. Here you are going with 2 of these instead of just 1, so that's why you have to increase this somewhat, because you're breaking that bond, right? Here what you were doing is you were just going from this to the ion form. Here you're going to the solid to the gas. So this Born-Haber cycle breaks down exactly the way in which how you go from something like this to something like this, and the overall energy that's released in the process. So it's a piecemeal, step-by-step process of going from one set of molecules or atoms to a final molecule. The next thing I want to talk about is the structure and polarity. Remember, like doesn't like. So things likes repel, opposites attract. So what we're going to, these are electron clouds represented by these bonds. And so what you're going to do is you're going to have those electron clouds trying to repel each other. So the best way for these to repel each other is to form a bond angle of 118 degrees, which will be about the same as this angle and this angle. Okay? And so what you're doing is you're looking at how long are these and what is their orientation in space. When we did those when we work on molecules in the lab we're going to have next week, you'll see that a carbon atom has 4 different locations, widely separated from where they each are, where you can put a bond. 2 of them will link together to this one, and that means that other remaining ones are off at these angles like this. And this is for the formaldehyde molecule, H2CO. Now, if it's something fairly simple, beryllium fluoride, for example, has 2 that are shared, and they're exactly 180 degrees apart. Okay? Because there's no other bonds for beryllium to share, are there? No other electrons for it to share. So these are going to be, it's going to be a linear one with 180 degrees between the 2 bonds. If you look at the more complex one and focus in on this, where you've got 2 regions, okay? This right here is a line dash model. This right here is a spatial arrangement model, seeing how things would look. And the ones that we're going to talk about are just these first 3. Okay, these are all going to be linear, right? These are all going to be trigonal planar. These are all going to be tetrahedral, okay? If you've got 5, then it becomes a trigonal bipyramidal or octahedral on these. But these will be the ones we'll concentrate on right now. You've got 4 regions of high electron density for these. These have 3 regions of electron density. This would be for a boron compound, and these would only have 2. This is for beryllium, or for some other instances where we have a double bond. Now, one thing I do want to point out, this is called the VSEPR theory, okay? So what they're talking about is the visual spatial electron distribution around here. So VSEPR means you are talking about this type of regions and geometries for them. Okay, so spatial arrangement and geometries. This right here is the tetrahedral. And remember, carbon can form 4 bonds, and this is how it would look like, where it's a tetrahedron with these at the 3 base parts of there, and this for the top part, right? So this is a PSChap structure. And so these are in the current plane. This wedge means it's coming out towards the viewer, and this right here means it's in the background. So here, if you've got a lone pair up here, that means you only have bonds down here. So that means you would have these 3 bonds right here plus that electron pair up here, right? This would be like nitrogen with 3 hydrogen atoms added to it. When you have something like this, this electron pair pushes away at this. So instead of the other angle that it has, instead of the 109.5, these right here are 106.8, okay? Slightly smaller than what you would have without this, the electron pair up here forcing them apart. And so here is the ones I want you to remember. These right here. You've got linear, okay? And this is electron pair is 0 right there, 0 lone pairs, okay, in any of these. So this is a trigonal planar, so it's all in one plane. These are 120 degrees. But if you've got 1 lone pair, it then becomes a little more bent, okay, down here, and you've got that one up there. This right here is tetrahedral. This is fluorine with 4 hydrogens or 4 chlorines or 4 something out there. And so if it has a lone pair, then this right here is going to push these closer together. This is going to be a little less than 109. And if you've got 2 lone pairs, it's going to be sort of an angle down here, okay? It's not going to be 108, and it's also certainly not going to be 180. Trigonal, let me see, which other ones do we need to look at here? Those are the major ones I want you to know about. The other ones down here, I will not test you on those, but you should understand at least what they look like. This right here, of course, is one where you're going to have just 180 degrees. This right here is going to be a trigonal planar, all of them in the same plane. This one right here is going to be octahedral, but this is the sodium ion. If there would have been the ammonium ion, if it would have been ammonia itself with just a lone pair here, these would have been squished together a bit more. This right here is oxygen, and it's going to have 2 lone pairs someplace, and it can bond to 2 other things, right? Or it could make this into a double bond right here. But whatever it is, if it's hydrogens, these hydrogens are going to be out there with these 2 lone pairs pushing these in somewhat. This right here, you've got lone pairs, and this is a bit more complex. What it's going to look like is the following slide. You've got these right here in the same plane along with this one. This was going to be in the same plane. These are electron pairs, unbonded pairs. This is going to be out, this is going to be out, this is going to be back, and this is going to be back. Okay, so you can see how this type of representation allows you to get a 3D image with a 2-dimensional figure. This right here is the polarity that we was talking about. You've got a covalent bond here, but a very different electronegativity between these two, and it pulls from the smaller number to the larger number. Likewise here from the larger, this is the most electronegative, so it's going to be pointed towards that one, right? Here it's going to be equal because these are both equal on this. And these bond moments are both going to be pointed towards this. Likewise, this right here, you've got oxygen, which is going to be more electronegative than this, and so the pull is going to be more in this direction than in this direction right here. And finally, we've got this one right here, where we've got 1 chlorine and hydrogens. The hydrogens are going to be pointed towards this, okay, and the chlorine is going to be pulled away from that. And in a solution, if you have electric field applied to it, are you actually going to get the orientation like this, as opposed to the way they would normally be